So 3.3, there's a couple of things we learned. Okay, we learned when the function's increasing or decreasing. So it increases when the first derivative is 4 would be an example of a positive number. Okay, and it decreases when the slope is negative, right? Okay, now we're going to learn about the curving upward. So this would be concave up, and curving downward is called concave down. So if you look at, I guess, this picture here, do you see how it's concave up from here to here? And it's also decreasing. And then here it's still concave up, and the graph is increasing. And here it's concave down, but increasing, and concave down and decreasing. So it can be any mix of those things. You're looking at how it's curving for the concavity. Okay, so the first derivative told us the rate of change. Now for concavity, we're going to look at the rate of change of the rate of change, or the second derivative. Okay, if the slope is increasing, the function is concave up. So if the second derivative is positive, it's concave up. If it's negative, it's concave down. So that's what we have here, the test for concavity. This is a huge test in calculus. It is. So if the second derivative is greater than 0, we're talking about concave up. And if the second derivative is less than 0, we're talking about concave down. And to determine intervals of concavity, it's very similar to how we determined if it was increasing or decreasing. So what you do is you take the second derivative, and we set it equal to 0 or find where it's undefined. So isn't that the same thing we did before with the first derivative? Now we're just doing it with the second derivative. Then we're going to use those x values to test the intervals. So we're going to put it on a number line. So we'll test intervals. And you look at the sign of the second derivative. If the second derivative is positive, what are we going to say? Concave up. If the second derivative is negative, we're going to say it's concave down. So do you see how this is very similar to what we did? Okay, but instead of first derivative, second derivative. Okay, so let's give this a try. This first one's a little bit tougher of a derivative, so that makes the problems, harder or easier. But a lot of them are very straightforward derivatives. Some of them are more difficult, like this. So first thing I have to do is take the first derivative, right? And there's a couple ways you can go about doing this. I'm going to move this x squared plus 4 to the numerator, so that's going to turn into what? To the negative first, good. And then to take the derivative, the 12 just stays alone. What happens to the negative 1? Bring it down front. Leave the x squared plus 4 alone, and it's going to become to the negative second, and then multiply by 2x. So this I could write as negative 24x, and then x squared plus 4 to the negative second. Then what do I have to do with this? Do the derivative. Now, what do I have to use to take the derivative? Product. So I've got this one and this one. So I'm going to leave the negative 24x alone. And the derivative of the other piece is what? What do I have to do with this whole thing? Bring down the negative 2, leave the x squared plus 4 alone. It's raised to the negative third. And then the inside of that is 2x. So that's leaving this alone, taking the derivative of that, right? And then plus, and what's the derivative of this? Negative 24. So you wouldn't really need the plus there, obviously. And then I leave this alone. Now I'm going to show you a little trick to make it, if we start, trying to multiply all this out and get all this stuff together, it ends up sometimes being a little bit more work. So if you can try to factor this when it's kind of in this form, and we'll clean it up a little before we do it, it keeps you from having to try to factor something at the end to find the zeros. First, let's clean this up a little bit. What are all the constants going to turn into? We got, yeah, negative 24 and a negative 2 would turn into 48, and then times 2 is the 96, right? So I have the second derivative equals positive 96 x squared, because I have the x here and the x here, and then I still have this. I'm just going to leave it like this. Okay, the other option you have, instead of doing it this way, if you're just really not good at doing it this way, is moving this down to the denominator, okay? And a lot of people do it that way, it's fine. And then back here, this is just negative 24 and x squared plus 4 to the negative second. And you would just move this to the denominator. And then what would you have to do if you're going to do it that way? Nope. You're not doing the derivative. You're just getting it, so you want to get the least common denominator and solve it that way. So that's completely fine. A lot of people do it that way. I just want to show you this other way because it's kind of a review of some of the stuff we've done before. What constant can come out of both of these? Okay, but the numbers here, 96 and 24. Does 24 come out of that evenly? No. Yeah, I think it does, doesn't it? No. Isn't it 4 times? No. Okay. So I've got 24. This x squared doesn't make it out, right? And then whenever you're doing, like, do you see how this has an x squared plus 4 and this has an x squared plus 4 to a power? What power do I choose? Nope. You choose the smaller one. Which one's smaller? Negative third is smaller than negative second, isn't it? Okay. So if I take that out of the front, this becomes a what? 4x squared. So that whole first piece is just a 4x squared, right? Back here, positive or negative? Negative. And this x squared plus 4 was to the negative second, so wouldn't I just need an x squared plus 4 to the first? Because don't I add these exponents and it would get back to here? So do you see how that's nice because it gets rid of the, weird negative exponent stuff in there? And then in here I just simplify as much as I can. So I've got 24 and then x squared plus 4 to the negative third. And then inside this parenthesis, what do I end up with? 3x squared minus 4. Everyone okay with that? And then typically we'd move this down to the denominator, right? So I'm just going to leave the 24 factored out, and I got the 3x squared minus 4, and then in the denominator I've got that x squared plus 4 cubed. Okay. Now with this particular problem, it probably would have been easier just to move this to the denominator, move this to the denominator, and get a common denominator. For some problems, it's a lot easier to do it this way, typically if there's not the negative exponent in there. And then it just factors it for you, so you don't have to factor it at the end. So I just wanted to review that with you guys. I would do it this way, especially if there's not negatives. Like if you have like an x squared plus 4 to the 5th and an x squared plus 4 to the 4th, I would definitely factor like this. Yep, you'd take out 4 of them in that case. Okay. All right, now what do I do with the second derivative? First, I'm going to set it equal to 0, right? So doesn't it equal 0 when the 3x squared minus 4 equals 0? So that would be when x squared is equal to what? Wouldn't it be 4 thirds?
4 thirds.
That's what x squared would be, right? Add the 4 over, divide by 3. And then what do I do to get x by itself? Square root. And when I do square root, I need to remember plus or minus. What's the square root of 4? 2. What's the square root of 3? Just square root of 3. So just leave it as 2 over square root of 3. You don't even need to rationalize it. This is fine. Okay, so that's when it's equal to 0. What else do I need to find? When it's undefined. And it's undefined when what happens? So isn't it undefined when the denominator is 0? Okay, now let's just try to set the denominator to 0. Subtract 4. When's that true? Never. So it's actually never undefined.
Oh, it's plus 4,
yeah, because if you put 2 in there, you just end up with, 4 plus 4 is 8 there. Okay, so it's never undefined, but you always want to check for the undefined spots. And then what do I do with my critical numbers here? Critical numbers is the second derivative. Close, we're getting there. We're not there yet. Number line. Okay, so we do our number line here. And I know these numbers aren't super nice, but that's okay. You still probably don't need your calculator, at least for this step. So this is 2 over square root of 3 and negative 2 over square root of 3. What's a nice number that's right between those? 0. Now what am I plugging into? If I'm trying to come up with concave up or concave down, f double prime. So I'm going to plug into here. If I plug 0 in, the numerator is positive or negative? Negative, and the denominator is positive, so it ends up being, what does that mean about my function? Nope. Second derivative. If my second derivative is less than 0, it's concave downward. Okay, so this is concave down. If you want to say CD, that's fine, right? But that stands for concave downward, okay? Now, pick a number that's bigger than 2 over square root of 3. If you're like, man, I can't do that mental math, I have no idea what that is, pick 100. Isn't that bigger than that? Yes. Okay, what's going to be true about the denominator if I put in a big positive? It's positive. If I put in a big positive here, it's positive. So this is positive. So that means it's concave up. Okay, and then put in a big negative number. What happens to the denominator? Positive, because it's squared. If I put in a negative here, isn't it also going to be positive if it's a big one? So I just have a plus here, so this would be concave up. And I think that's all I was asking for, right? Concave upward or concave downward. So then we just want to write it so it's very clear here. So concave upward. We're going from negative infinity to negative 2 over square root of 3. And then where else? 2 over square root of 3 to infinity. You can't go beyond infinity, so I do. Okay, so concave downward would just be negative 2 over square root of 3 to positive 2 over square root of 3. Do you see how you can do that without your calculator, even though it was, really weird numbers? Yeah. Okay. Yeah, let's take our break and then we'll come back. Okay, second page here. It talks about this key word here, keywords, point of inflection. Okay, so if a tangent line to the graph exists at a point where the concavity changes. So do you see how the graph is concave up here? And then it's concave down here? Where it changes concavity, that's called a point of inflection. Okay, so it changes from concave up to concave down, so this would be a point of inflection there. Same idea here, concave up to concave down, or it could switch from concave down to concave up, okay?
Just like draw a line between the two endpoints, and that's where it is?
No.
In this.
Maybe in this particular one. You find where it changes concavity. So like back here, if we look back at this problem, didn't it change from concave up to concave down at this spot? This would be my x-coordinate for a point of inflection then, okay? So let's just do the example. So definition of a point of inflection is where its concavity changes from up to down or down to up. Okay, so let's try to find the intervals where it's concave up or concave down and then find the points of inflection. So first thing I need to do is what? Derivative of the derivative. So first derivative is okay, then I need the second derivative.
12x squared minus 12x.
Does that look right to everybody? Then what do I do with the second derivative? Find when it equals 0. So it equals 0 when, what can I take out of both of those? 12x times, no, if I take 12x out, it's x minus 1. So it's when x is 0 and x is 1. Then what do I do with those values? Number line. And what am I plugging into for concavity? F double prime. Okay, I'm going to plug into here instead of into the second derivative that's written above, just because it's quicker, and they're equivalent to each other, so it should be fine. If I plug in, let's say 2, something bigger. If I plug in 2, this is positive, and this is positive. If I plug in a half, this is positive and negative. If I plug in negative 1, this is negative and negative. So does everyone see how quick that is? And then what goes down at the bottom of the number line? F of x. So if the second derivative is positive, f of x is concave up. Negative is concave down. Positive is concave up. So let's answer the first part where it's concave upward and concave downward. Okay, so we've got concave upward from negative infinity to 0, and then from 1 to infinity. And concave downward from 0 to 1. So is everyone okay with that portion of it? And then here's the new part, is my inflection points, or points of inflection. So where does it change concavity? At 0 and 1. So points of inflection are going to be 0 comma something and 1 comma something. And how do I get the something that goes with that? Plug it into the original, okay, because you're trying to find the point on the original graph where it changes concavity. So if I plug 0 in, I get 1. If I plug 1 in, I get?
1 minus 0.
So 0, right? So that would be all of the pieces that they were looking for there. Or usually it's called an inflection point. And points of inflection is the same as inflection point. So a lot of times points of inflection I call IP, inflection point. Okay? Okay, so any questions on that second one? Okay, we're going to do the second derivative test. This test is, it's not difficult, but a lot of people kind of forget about it because they get so used to doing things this way just because that's what we've done. Sometimes the second derivative test just makes problems way quicker or way easier. So second derivative of a function can also be used to discover the nature of the relative extreme points. So it'll tell you if it's like a max or a min. So this is a different way to come up with that. So second derivative test. If the first derivative equals 0, and the second derivative exists on the open interval, then if we know the second derivative is greater than 0, there is a relative min. And if the second derivative is less than 0, then there's a relative max. And we'll do an example here. If the second derivative is equal to 0 at that spot, then the test fails. Okay, and then you have to go back to the first derivative test in your number line to see whether it's a max or min with the increasing and decreasing. Okay, so let's actually try this example and see what happens. So first thing I need to do is to find the first derivative, set it equal to 0. So my first derivative is minus 12x squared. And I want to find when that equals 0. What comes out of both of those? 4x squared, and what's left? X minus 3. So when does it equal 0? When x is 0 and when x is 3. Now you don't have to do the number line for the second derivative test, okay? So first thing is find when the first derivative equals 0, and then we're going to find if the second derivative is positive or negative. So now we take the second derivative. What is the second derivative? 12x squared minus 24x. And I plug in these two values here. So I'm going to do f double prime of 0 and f double prime of 3. So if I plug in 0, I get 0. And if I plug in 3, close, 36. So any questions on what I've done so far here? Do you see how this is fitting exactly what it's telling me to do up here? First derivative equals 0, we did that. And then the second derivative, plug in those values. Okay, so second derivative, if it equals 0, what happens? Test fails. So here, this part here, the test fails. Okay, if the second derivative is greater than 0, what's true? There's a relative min. Okay, so then I would just say, let's see, find all relative extrema. I would say that there's a relative min at 3 comma something. How do I find the something? Plug it in the original. So don't just say 336, okay? It's 3 and then it's what's in the original. Negative 26. Okay, so I know there's a relative min there. Now what does it say about if the test fails? Use the first derivative test. And the first derivative test, so if it fails, we're just going to see what's going on at that spot. So that was the little number line piece here. So that was at 0 and at 3. Now I know at 3 there's a what? A minimum. So that means the graph must have been decreasing and then increasing, right? So this would be my first derivative. Now if I plug in something less than 0 into my first derivative, so let's plug it into here. If I plug in a negative, this is positive and this is negative. So what's happening? Is there a max or a min there? No. So that's actually what's happening at that failure spot there. Okay, so this, yep, doesn't give us an extrema there. So this is the only one. So that's just a way to double check to make sure that, you know, you're not missing that one. Okay? All right. So ready for the last bit? Okay.
We had every answer possible.
So in economics, which is a lot of where you're going to use calculus, or a lot of business people, you know, use calculus, there's a concavity is going to show us where diminishing returns is going on. So what that means in terms of calculus is it changes from increasing concave up to increasing concave down. So it's an increasing function, and it changes from concave up to concave down. So this would be my point of diminishing returns. And what that means in economics is if the function is concave up like this is, isn't the slope getting steeper and steeper? Okay, if the slope is getting steeper and steeper, that means each dollar invested is returning more than the previous dollar, which is good in economics. Okay, if you invest $1 and you invest $2 and it's giving you more back, that's better, right? If the function is concave down, each dollar invested is returning less than the previous dollar. So an increased investment beyond the point of diminishing returns is usually considered a poor use of capital. So you want to find this point in economics, and that's exactly how much capital you want to put into that investment. Okay, so it actually does get used a lot for, like, you know, bigger companies where they're actually looking at that to save themselves millions of dollars or to earn themselves that extra bit of money. Okay, so here it says find the point of diminishing returns for this model, where R is the revenue in thousands of dollars and X is the advertising cost in thousands of dollars. So what do we have to do in order to find this point of diminishing returns? Yep, and what derivative do I need? Second, because I'm talking about the concavity. So whenever you're talking about concavity, you're going to be talking about the second derivative. So isn't this just a constant out front? There's two things you can do with that. You can just leave it out front and kind of, you know, leave it there, or we can multiply it through to the two pieces. I'm going to leave it just because it makes sense too. So if I leave the 1 over 20,000, and then I take the derivative of the inside, what do I get in here? 900x minus 3x squared. Sounds good. And then I need the second derivative, right? There we go. Okay, so taking the derivative of this, I leave the constant out front, so 1 over 20,000. And then the derivative of that inside stuff is 900 minus 6x. And then in order to find the concavity, I want to find where the second derivative is what? 0.
See how far that is. See how far that is.
This is going to equal 0 when what's in the parentheses equals 0, right? So when the 900 minus 6x equals 0. And then I would add the 6x over, so I get 900 equals 6x. And then solve for x, divide by 6, right? So what do I get? 150. And remember, x is the advertising cost, so this is our advertising cost. What do I do with that critical piece there? Put it on your number line. And what am I plugging it into? Our double prime, right? Because I'm trying to find the concavity, so I can find that point of diminishing return there where it changes concavity, that inflection point. So if I plug in something less than 150 into the second derivative, so if I plug 0 in, I end up with a positive. So that means my R is doing what? Concave up. And then if I plug in something like a bazillion, it's going to be negative. And that means it's concave down. So isn't this my inflection point? Which is also in this economics, as long as it changes from concave up to concave down, I know that it's a point of diminishing return, right? So let's see, find the point of diminishing return for this model. So I'm just going to go ahead and write it out here. So therefore, the point of diminishing return for the product, you wouldn't have to write all your answers out like this. This is just so we're actually understanding what's going on in the notes here. Occurs when the advertising costs are what? And I heard 150. What would be my label for that? In thousands of dollars. So it's not just $150, it's $150,000. Okay. It's pretty much what I make every year, so yeah. So you know what I do? I advertise, you know, get more people in my classes. Okay, so any questions on that? All right. There's your homework.